Hi, my name is Kaleb Schaf, and I am a senior electrical engineering major here at Trine University. And today I'm going to be talking about my senior design project, which is a fully autonomous lawnmower. I was paired up with another electrical engineer and a computer engineer to make a mower that will safely mow the yard without any accidents, such as bumping into something, running over something, and also return home back to its base where it will charge. The first thing I'm going to be talking about today is the buck converters. So this is part of our power system, and the way this works is it will step down from 12 volts to 5 volts using a switching method that ensures that no matter what load it is getting, whether it's getting a current of 5 amps or 25 amps, it will stay the same voltage without any issues. And we are going to have a couple of these on board. And as you can see on the back, we have out pins and then in pins. The N positive will be the positive rail of the 12 volts, and then the N negative will be ground. So anything you want in between these as a circuit will go in between this. So for our purpose, we will be having motor drivers, which are used to control our motors using a pulse width modulation signal. And this signal will allow us to turn the motors, whether we want them to go at full load or half load, along with letting them go backwards, which in our case for our motor, when we detect an object using ultrasonic sensors, which I will get to in a minute, it will back up and turn without having any issues. Now on the other side, we have the out pins right here, and with these, this is used for the 5 volts. So we will put a 5 volt rail out the out positive for power, and then we will have out negative, and that will be ground. So for our purpose, we will be using this for our bump sensors, our ultrasonic sensors, our compasses, our microcontroller, and our boundary wire signal for detection. So that's what these are for, and I also have a very large 48 to 12 volt, which is then powered to this. Next, I'm going to be talking about these ultrasonic sensors, and these are going to be used for object detection to ensure that we don't run into anything. For our project, we are using the HCSR04s, and as you can see, there are 4 pins. One is the VCC, the trigger, the echo, and the ground. So these are the 4 pins that we'll be using to control them. The VCC and the ground are the power ones. The VCC will connect to 5 volts, and the ground will connect to ground. And the way we're connecting these, we are using a PCB with header pins, and with these, we will connect it inside. And with how these work are on the bottom are little copper pads, and we solder them on there, and each copper row is connected. So this top one right here is also connected to this. So if I wanted to put 5 volts here, 5 volts would also be here along with ground and ground. So when I'm powering the ultrasonic sensor, I'm going to be getting a pulse like this. This 10 microsecond pulse is the smallest pulse I can send for this to work. So for our case, we're going to be sending a 10 millisecond pulse, and if I were to measure between the trigger pin and the ground pin, this is what I would see on a scope. After that occurs, a little sonic burst will be sent from the module. There is no way to see this. This is a little invisible signal. But after it's done, the echo, which is the other pin I showed you, will output a 5 volt pulse. And the way this works is we made a program that will measure from the rising pulse edge, which is this edge right here, to the falling edge, which is the edge right here. And we will be using an equation for the velocity to get it to centimeters. So as we can see above, it's the high level time times the velocity, which is 340. Then we divide that by 2. And this will convert it to centimeters, which we will use to determine how far we are away from an object. So for this pulse, it will get smaller the closer an object is, and larger the farther away it is. The last thing I will be showing you is my MOSFET switching circuit. So a MOSFET is something that can be used as a switch in my case, which I will be using, and it has 3 pins. It has a gate, a drain, and a source. And for my instance, the source will be ground, the drain will be connected to my motor, and the gate is where I supply the power. So when I supply 12 volts to the gate will cause the switch to basically close, and the motor will go from, or the drain will go from 48 volts to 0 volts, which means there will be 48 volts across my motor which will cause it to turn on. Now, when I turn off the 12-volt rail, this will mean the gate is getting 0, which will open it, causing the drain to source voltage to be 48 volts again. This means that the motor will not turn on. So for this, I am using what we call a relay. So this relay has 3 pins on this side, which are VCC, then there's an input pin and ground. So ground will go to ground, VCC will go to 5 volts, and then there is a logic input, which is a 3.3 volt input from our board. So when I make the pin high, this will cause the switch inside here to close. This will then cause from going from here to close, which will mean they are connected. Now, when it is low, this will cause this to open, and these two will no longer be connected. So this will be how I will be turning on and off my switching circuit. Then we have these 2 chunky diodes right here. So the 2 outer pins right here and right here are going to be the anodes, and they share a common cathode. The goal of these is to protect the MOSFET, so protecting this. Because when the motor turns on and turns off multiple times, it could cause back EMF, which will cause this to always be conducting, meaning it is always going to be on. So that'll be an issue. So I'm using these to help with voltage spikes, allowing it to constantly turn on and off without any issues. Then you have 2 resistors. You have the gate resistor and the pull down resistor. The pull down resistor is used to ensure that it does turn off, and the gate resistor is to ensure that it is not being fried as soon as I put current and voltage into the gate. So this is how I am controlling the blade of our motor, which is a very large 48 volt and can draw up to 10 amps. So when doing this, you need to ensure that you are getting a properly rated MOSFET. Mine is rated for 55 volts and 110 amps, which will be just fine. So thank you for listening to this, and I hope you are considering Trine University, as it is a great place for learning and then doing projects. Thank you.